Okay, so we looked at the experimental evidence that suggested that fatter hyperplanes are better, but now we're looking at the theoretical justification. And for the theoretical justification, what you're looking at is the VC dimension of these fattest or optimal hyperplanes, essentially. Okay, so what we will try to focus on is that the VC dimension of like a fatter or an optimal hyperplane is smaller than the VC dimension of the thin hyperplane, because when that happens, then of course we will get a tighter link between E in and E out. And in that sense, my optimal hyperplane or my fattest hyperplane will definitely be better than my thin hyperplane. Okay, so for that, we are considering this like very simple data set that has like 3 points. So here, here, and here, all 3 points. And there are 4 dichotomies as shown. And you can just like by looking at the data set tell that a perceptron can shatter all 4. And it's not just like restricted to these 4. If we flip the blue and the red lines, like the blue go like all the blues were this side and they were red, right? And similar to that, like flip this versus this, we'll get 4 more, which is like total number of 8 dichotomies, right? And so perceptron will be able to shatter them. And if we like if we go back to the definition of a perceptron, we know that a perceptron is a separating hyperplane with width 0, right? That's what a perceptron is. It is separating the data, except that it has no width. All right, so what we are trying to do is we are trying to understand the VC dimension of my fattest or optimal hyperplane. So let us assume we have a hyperplane with some width, and then we try to separate this like same data. Okay, so let me show you another picture here, the exact same data, but this like yellow thing is essentially the hyperplane, and this is the row, which is like my width, right? And if we look at this picture, the first 2 dichotomies, this one, number 1 and number 2, they can still be separated by this fat hyperplane or my thick hyperplane. But if you look at these two, right, the perceptron was definitely separating them, but these two cannot be separated by my fat hyperplane because I have this like fixed thickness of this and I cannot do anything about it. So once I have a fat hyperplane, I just have it and I cannot just like do anything about it. And so that's why these data points, as you can see, lie within that thickness. And this is not what we wanted. From the definition of the separating hyperplane and from the definition of the optimal hyperplane, we want this to separate the data and not like include the data. So one way of dealing with this situation is to move these data points further apart. How about I'm able to move these like outside as far as possible from one another? And but if our input space is bounded, I have like a certain bound on my input space that I cannot go beyond this point, right? Then of course I'm not allowed to move the data. So of course in that case the solution cannot be implemented. Therefore, a fat hyperplane cannot implement all dichotomies, as I can see just by looking at this like toy example. Now, if we can move the data, then maybe we can. But if we cannot move the data, if my input space is bounded and my data is maybe close together, by bounded I mean the data is close together, then I cannot really implement or I cannot like separate the data in these two cases. So let's say this is like by bounded, I mean that my data is bounded in a sphere of radius r. And if that is the case, then what we're looking at is some ratio that is r over the thickness of which was gamma. This is like what we used when we were like denoting the thickness of the hyperplane. So we can infer then that this ratio will play some important role in determining whether we can separate or not separate the data, right? And it turns out that the VC dimension, which is like the maximum number of data points that can be shattered by a hypothesis, has some relationship with this ratio. And that ratio and that relationship is a theorem. So let me first state the theorem and try to understand the intuition behind it. So what this theorem states is that the VC dimension for this hyperplane with thickness gamma is less than or equal to the ratio of r squared, which is like the radius for the bounded input, like the data, over the thickness squared plus 1. Right, so this is the thickness of the hyperplane. let me just repeat it, thickness of hyperplane. And what is this theorem telling us? This theorem is telling us if your data is bounded within this sphere of radius r, which is my numerator in this case, and you're like, imagine your thickness is getting larger and larger, so your denominator is getting bigger, right? If this gets like really huge, right, then you cannot separate anything and just like implement the two dichotomies that are there. So this is what this like essentially this theorem is stating, or this theorem is essentially telling us. This is also telling us that if your data is bounded, then your thick hyperplane can have a lower VC dimension because you don't have all the possibilities there, right? And so if you have a lower VC dimension, if this is lower, right, then the good news is that you have a tighter link between E in and E out, right? And in general, about any hyperplane, we have some information about the VC dimensions of a hyperplane. Here we like kind of derived this, and like this was just like an intuition. We didn't mathematically derive it, but this intuition kind of told us that this VC dimension has uh, a dependence on this ratio. But in general, we know about all hyperplanes. For any hyperplane, in general, we are aware that the VC dimension of any hyperplane is at most d plus 1, where d is the dimension of my feature space. And so if we combine both these statements, the final theorem is like stated something like this, that the VC dimension of my hyperplane is the minimum of these two quantities, which is like d plus 1 or r squared over gamma squared plus 1. And of course, you can take out the plus 1, and so we are essentially finding the minimum of d, or this ratio, plus 1. So this theorem states that if we have a fat enough hyperplane, if the thickness of the hyperplane is enough, and your data is bounded, then you can get a small VC dimension. And think of an extreme case when gamma, as I said earlier, is getting bigger and bigger and r is getting smaller and smaller. Then what is happening to this ratio? Like my gamma is extremely big and my r is small, right? So there will be that point that will lead us to a VC dimension that approaches a constant. And that constant means it's independent of my data dimension. And this suggests that by using a fat hyperplane or a thick hyperplane, we can get better generalization even in large dimension, because my VC dimension is getting independent of dimensions, which is great in this case. All right, so this theorem gives us a theoretical intuition behind why fat hyperplanes are better than the thin ones, because of the VC dimension getting almost, in certain cases, the possibility of like getting a VC dimension that's independent of data dimension, and that is pointing towards very good generalization. Okay, so having done this theoretical intuition, let's now try to prove a result that is practically relevant. And that in practice links optimal hyperplane to the cross-validation error. So we'll see how support vectors play an important role when we are looking at cross-validation error. If you remember, cross-validation errors were a really important component when we were trying to do model selection, right? So what we're looking at is the cross-validation error, or ECV or CV error, whatever you like to call it, of maximum margin separating hyperplane, or of maximum margin fattest hyperplane. Let's look at what this gives us. Okay, again, a quick review of what this cross-validation error was. We were trying to determine the error by leaving one point out and getting the average of all those errors, right? That was what cross-validation error was. And essentially training the data on the rest of the points, taking one out or leaving one out, computing the error and getting the average. So we also found that this cross-validation error, right, was an unbiased estimate, of E out that was calculated on n minus 1 points, right? So in other words, cross-validation error is so important that through this cross-validation error, we have some handle on E out. We have some kind of a relationship with E out, and we know that if we can do something about this cross-validation error, if we can control cross-validation error or affect cross-validation error in some ways, we have a handle on my E out. So that's why it's so important. And what we are trying to prove here, the result that we are trying to prove is this, that my cross-validation error for the fattest hyperplane or the optimal hyperplane, fattest hyperplane, is at most, like this is bounded by this ratio of number of support vectors divided by n, where n is the number of data points. All right, so let's look at this illustration with a few data points and see what is this like, what exactly is happening here. So the numerator is like the total number of points, of course, and let's say we have like some data points like this, and this is this, and we know that these are the support vectors. Let's say these are the support vectors. Let's assume there was one more here, right? And then you have the separating hyperplane going here. So this is my support vector, this, and this. Okay, that's really bad drawing. But the whole point of showing you this drawing is that the support vectors are determining my hyperplane, as we already know from the definition. And so they are like the most representative part of my data. So they are the important data points. And we know that if we throw away these other points, right, like we will still have effectively almost the same separator. And we've looked at this before. So the point that we're trying to establish here is that the final hypothesis does not change if you only keep the support vectors and you throw away the rest of the data, no matter what that data is, right? So support vectors are important data points. All right, so let's say what we're doing now is that we are continuously generating more and more data, right? And then getting these separators again and again, because that's how we're going to get the final optimal separator, right? So sometimes a new point will lie within the margin. So it may lie here, right? Sometimes it may not lie here. It just like depends. And every time what we're doing is, this situation will happen less often, obviously, right? So the number of support vectors will remain almost constant. Sometimes they may change because a new point comes in there, but most of the data will be like added here. Most of the data will be added outside. So the point I'm trying to make is that my n will increase more than my number of support vectors, which means like this denominator here is increasing faster, right? And as compared to the numerator. And so my cross-validation error is dropping, right? Is dropping, it's becoming smaller and smaller, almost to zero, pointing to so if my ECV is becoming small, this points to a lower E out, right? So my E out is also small. Why? Because my cross-validation error is an unbiased estimate of my E out. So that's like number one observation. Another important observation is that there is no explicit dependence on dimensions here, as you can see. It's just that I'm like adding data and like checking the support vectors and getting the hyperplane, that's it. So this in turn tells me that it might happen that in higher dimensions, like the number of support vectors can go up, but as long as they are increasing less than my n, if they're not increasing as much as my n is increasing, then in that situation, I can keep my cross-validation error in control, right? And so in turn, I can keep my E out in control, right? So that's the fundamental idea behind creating this relationship of what do you call it? Cross-validation error with the support vectors. All right, so of course we have this here, but we need to prove that this indeed occurs. This is all good, of course, but we need to prove it, and let's do that proof. Okay. So in proof, what we're doing is, again, let me consider some data points, right? And okay, that's that. And these are here. let's say this was my support vector here, this is my support vector here, and this is like another point. So these are my support vectors essentially, right? And then I have a hyperplane up here. Okay, so imagine we are leaving one, as we are like learning, we begin with this hyperplane and leave one point out, right? And if we leave one point out, our final hypothesis, well, changes sometimes, sometimes it doesn't change. So what exactly am I trying to say? In other words, my hypothesis like correctly classifies the left out point, although it's left out. Okay. So again, let me show you what I'm trying to say. Because the cross-validation error is calculated using like leaving one out. So let me assume this was the point that I left out. And I'm calling it like leave out or leave one out, which is also termed as like LOO, right? So this is that point. So if I left this point out, is this really is not impacting my hyperplane, which is this, right? So if I left that out, it's not impacting my hyperplane at all. So again, my final hypothesis is not changing. My hypothesis correctly classifies this left out point, although this wasn't included in when I was determining my hypotheses, which in turn tells me that this error, as a result, this error, leave one out error, as a result of this point, let's say this point was x, which was not a support vector, is 0, right? All right, so again, let's say in the next iteration or like whatever I'm doing, let's say I left this point out. So this is my left one out. And then the error for left one out when this point is a support vector will be finite, because what happens is like non-support vectors mostly will not contribute anything, so my hypotheses will not change. This can or cannot impact. Maybe it will not impact, but it can impact, so it will have some finite value, which at most can be 1, but not more than that. So this is like the at most. Okay, so then by definition, my cross-validation error is the average of all the errors over all the data. So I have, let's say, endpoints, n equals 1 up to n, e leave 1 out for all xn's. But remember, the xn's that are not support vectors are not really contributing to the sum because they are 0. So eventually this turns out that this becomes 1 over n is, so again, I would just like remove this n from 1 to n and instead say sum over all support vectors, right? And then leave 1 out x support vectors, right? And the max this can take is 1. That's the max possible. So what I'll do is sum over all support vectors, and this, let's say, is 1, which is nothing but the number of all support vectors over n, which is like the denominator here, this one. All right, so this is my end of proof. This is what I wanted to prove. Okay, so this kind of shows we might be able to control E out somehow, because first of all, I have this like upper bound on my cross-validation error, which is dependent on the number of support vectors, and the number of support vectors are always like much lower in number as compared to my data. And if we can leave one support vector out and calculate the cross-validation error to get the actual value, and not just like an upper bound, then we have a way to keep E out in control. And this in itself, like getting some, like utilizing cross-validation error to get some control on E out, is a very powerful result. All right. So again, let me put all these points together, and oops, I should have added one more slide here because we need it, of course. Let me keep this and let's add a new slide. Okay, maybe 2 more slides because I just like wanted to summarize everything before we end this part of the lecture. So in general, like if we think about hyperplanes, we know about like the perceptron, right? We are aware of the perceptron. And what does a perceptron do? Well, it has this like VC dimension exactly equal to d plus 1. Remember, we proved it. And so this kind of links E in to E out efficiently because we can establish the first step of learning. Now, currently what we are analyzing is that an algorithm that determines the fattest hyperplane hypotheses and also has some like relationship of the VC dimension with some other aspects of the data, right? And this means like what we're doing right now is we are focusing on a very special type of a hyperplane, which is like, again, perceptron is also a hyperplane, right? And we know some properties of the hyperplane, of course. And now because we are exploring a special type of a hyperplane, which has some thickness as well. So although we have like extended the definition to select the fattest, but some of those things still apply in general, right? So that's some small observation that I just like wanted to add here. Or perceptron is nothing but again a hyperplane with a zero width. Okay. Now when we are like focusing on the optimal hyperplane, which is like the fattest possible, these are some of the properties that we looked at. And again, as I said, I wanted to summarize them. So the first thing was experimentally we saw, so experimentally what we saw was my bias with my optimal hyperplane of the fattest possible, my bias goes down, but my variance goes down a lot, right? It went down a lot as we could see in the experimental analysis. And so that in turn points to the fact that my E out, which is effectively a sum of bias and variance in certain situations, will also go down, right? Experimentally, we saw that with an optimal hyperplane or the fattest possible hyperplane. The second property that we looked at was the theoretical intuition of getting the VC dimension less than the min of D and R squared over gamma squared plus 1, right? And so what this was telling us was that we can achieve a very low VC dimension because here our hypothesis is defined by deciding the thickness, which means in some sense we are looking at the data, right? So of course there is some work that's needed to establish the exact link between E in and E out, which we are obviously not doing here. But the important point here is that this fat separator have like less separating power as we saw earlier when the data, especially when the data is bounded and you cannot really, do much about it because it's like really tightly packed. But the good thing is that then in that situation, like it does not depend on my data dimension, which is D. And so what this is like telling me is that of course I couldn't create an exact link between E in and E out, right? I couldn't exactly do that. But in some ways, right, let's say in higher dimension, I can control E out because I'm like really getting out of the dimensional trap, right? So this is what this intuition was telling us, the second theoretical intuition. And the third, I would say one of the most important observation was this cross-validation error, that we could come up with this bound of like the number of support vectors over my n. What was this telling me? This was telling me that I can get some control on E out even in higher dimension, because like if the number of support vectors is bounded and I have like some way of like dealing with it, right? And of course, like there will be a situation where the number of support vectors usually will stay lower as compared to my n, then of course I have a very good handle at my E out. And that's again an excellent result. And the fourth thing was that how are we getting this? How are we like really getting the final fat hyperplane? Well, I'm using this algorithm, which was again an effective algorithm. It's a quadratic program, and so I'm trying to solve that essentially, right? And comparing this to my like very well known PLA model, right? Let's see if we have space, of course. So if I still compare it with PLA, which is again a hyperplane, even PLA is not as bad, and that's why we were seeing good results. So in PLA, we can theoretically establish some ways that we have this like cross-validation error that's bounded by R squared over the data times gamma squared. Yeah, this gamma is essentially the thickness of the optimal hyperplane. Okay, so of course, this is not as clean as the optimal hyperplane itself, but like you can tell that there is this relationship, right? And that exists, and that can help us get good results, right? All right, so this was all about the properties of the fattest hyperplane. and about establishing the fact that the fattest hyperplane is indeed better. But there is something that I would like to point here, that until now we've talked about this separable data, right? And we've been creating these hyperplanes in linearly separable data. So now the question arises, what happens if the data is not linearly separable? Like there could be a nonlinear problem. And so that's something that we're going to look at in the next video. So I'll just end it here. Thank you.